Mining is a temporary land use, so having found, evaluated, designed, planned and operated our mine in a safe and environmentally responsible way, it remains for us to tidy up and then to hand the land over to some future productive use. There is a societal expectation that post-mining the land will be returned to some form of productive use, commensurate with the productivity that it had pre-mining, although it may not be the same use. This land use should be viable for the long term and not just the short term. Some regulators strictly define what is meant by long term and require viability guarantees for up to 1,000 years, although periods of 100 to 200 years are more common. There are a number of issues beyond the immediate clean-up of infrastructure and waste on the site that require management to achieve these issues. They are broadly described under the headings of final landform design, tailings management, final voids or open pits, ecosystem viability, and on-site versus off-site impacts. The final landform refers to the shape of the ground left behind after mining concludes. When rock is mined and crushed, its volume increases by up to 20 to 30%. This is because what was solid rock has now many voids. This means that the pile of waste rock produced, even accounting for the material shipped off-site as product, is greater than the size of the hole that was dug to produce it. As a consequence, there will almost always be some form of mined waste structure above the natural ground surface, and this structure needs to be designed to be stable and sustainable post-mining. Because this structure is higher than the natural landform, it will be steeper, so that runoff velocities and erosion rates will be higher than pre-mining, unless runoff and erosion protection measures are undertaken. Accordingly, hydrology and erosional stability of the final landform is a major consideration in landform design. Most mines find that a significant proportion of the cost of rehabilitation are the costs of the earthworks required to construct the final landform. So significant cost savings can be made if the shape of the final landform is taken into account when waste rock is dumped during the operation of the mine. From the regulatory perspective, this cost is incurred at one of the least financially viable periods in the operation of the mine, that is, when the mine is about to close and profits from production are low. There is a risk that a mining operation can become bankrupt before a rehabilitation is complete. To offset this risk, regulatory authorities may require the lodgement of a sum of money, a rehabilitation bond, that is equal to the likely cost of rehabilitation at the end of the mining. Final landform may contain a large range of wastes. Waste rock, which is a more significant issue for surface mines than underground mines. Below-grade ore, which is rock from the ore body, but where the ore concentration in the rock is too low to make extraction economic with current prices and technology. Crusher reject, which are rock fragments of mostly gangue minerals removed from the crushed ore during beneficiation. Tailings, which is fine-grained waste from the beneficiation process. And pyritic waste, which is waste containing mineral sulfides that can oxidize in the atmosphere to leach acids. Tailings are often pumped into tailings repositories akin to dams. As tailings are mud-like, they have a very low strength and a very low erosion resistance, at least until they're dried, and this may take many years. Tailings disposal is typically the most difficult part of assuring the long-term safety of a final landform. If tailings are exposed, they can produce a significant wind erosion hazard. Commonly, at mine closure, tailings repositories are protected by a rock cap up to a couple of metres thick. If the repository is constructed above the land surface, there is the potential for erosion of the cap and exposure of the tailings. This animation is a computer model of erosion taking place in a cap over a tailings repository. If erosion is deep enough to reach the tailings, the rate of erosion will increase because the size of the tailing particles is very fine. Any gully eroded into the cap will rapidly expand, undermining the cap, potentially leading to catastrophic failure of the tailings enclosure, as can be seen in the photo. If eroded, the fineness of tailings means that they stay suspended in aquatic ecosystems and they are potentially chemically reactive, and so there may be implications for water quality downstream. To reduce this risk of exposure through erosion, it is common at mine closure to move the tailings back into the pit, but this is expensive. There is also the potential risk that the tailings may interact with any groundwater structures that are intersected by the pit. To assess the possibility of this, it is necessary to undertake regional groundwater modelling. Many open-cut mines end up with a final pit or void that is left open after mining finishes. This void will fill up with water from rainfall, leachate from mined areas, and runoff from natural areas. Final voids have, in the past, become highly saline and/or acidic over time. Hence, a water-filled void is also a potential source of pollution for any groundwater systems that the pit intersects. Sustainable ecosystems on the final landform are a desirable output. They should be compatible with the adjacent land uses, otherwise they may become a source of feral flora or fauna. Grasses provide significant protection from erosion. Much of the long-term viability comes down to the robustness of ecosystems for self-seeding and their ability to survive extreme conditions such as droughts and fires and floods. It is generally assumed that if rehabilitated land is viable in the short term, then it will be viable in the long term, although there have been cases where this has proved not to be so. Ideally, the landform created should be stable over the long term, say from 100 to 1,000 years, and to do this it needs to mimic the shape of natural landforms. The problem with this, however, is that the processes that shape natural and constructed landforms are different because the ground conditions are different. Thus, the equilibrium landform shapes will be different in the two cases. Most of the soil and ecosystems on constructed landforms are changing over time, so the stable landform itself may change over time. To solve this problem, it is becoming common to use landform evolution computer models to simulate the long-term fate of the constructed landform. The most commonly used is the Siberia landform evolution model. So that's the mining process in a nutshell. In the modules that follow, we will focus in greater detail on what mining engineering as a professional discipline is all about.